Well, today we want to continue our discussion on, well, we're leading up to talking about acceleration in more detail than we did last time. Last time we said, well, the second derivative of position is going to give us the acceleration vector. But today we're going to look at components of the acceleration. To do that, though, we need to talk about a couple of things. One, a couple of unit vectors. The first one is the unit tangent vector. So what I've got here is I've got a nice vector valued function sketched here, this curve. And its values are, well, I have for the x t and then t squared for the y part. So pretty simple vector valued function. Now what I want to do is I want to get the derivative of this. In other words, I want to get the vector that's parallel to the tangent vector at 1. So I'm going to do this. I'm going to say r prime of t, and of course that's 1 comma 2t. Now I want to get the specific vector at t equals 1, so I'm going to do this. I'm just going to say r prime of 1, and I get this. Now remember, the way we are sketching these velocity vectors or the derivative vectors is we're using the initial point. I'm going to use the initial point 1, 1, and then go from there. I'm going to go over 1 and up 2. Okay? That's the way we've been sketching these. So that's the way I'll do here. So I've got 1, 1, I'm going up 1 and over 2. And there is my a vector that's parallel to the tangent at t equals 1. Now, what I want to do at this point is just see if we can figure out, let's suppose that we want another vector. Let's suppose we want a vector that's normal to this vector. In a vector, in fact, that goes into the concavity. So we've got this vector here, 1, 2. And now remember, when I say normal, I'm saying when we dot product that vector. So I've got this vector here, and I want to dot product with some other vector. And I want the result to be 0, right? When you dot product the vector, you get 0. So what can I dot product this vector 1, 2 with to get 0? And I want it to be such that it's perpendicular to this vector inside the concavity. What do you think? Okay, so let's look at this. Let's suppose, so we could say this. We could say, okay, this is negative 2, 1. And notice, yeah, if you dot product, if you say 1, 2, and you dot product with negative 2, 1, yeah, you get negative 2 plus 2, and you get a 0. Now, we need to pay attention to something here. Notice the similarity between these two vectors. Right now, we're just talking about a tangent vector and a normal vector in the plane. And notice that this one is 1, 2, and this is negative 2, 1. Notice how that we have just swapped the x and the y and changed the sign of the first term there. So that's something we need to pay attention to. But let me go ahead and plot that vector now. If I come over here and plot this vector, I'm going to go over 2 and up 1. And, you know, it doesn't look exactly 90 degrees there, but you can see, yeah, that must be 90 degrees. So what we have here is we have a tangent vector, a tangent vector, and we have a normal vector right there. So this is what we're going to talk about today for the first part of class. Now, you notice that this tangent vector here is not a unit vector. So we have both magnitude and direction for this thing. Well, I want to change that into a unit vector. So in fact, I want to do this. I want to say, okay, this vector that I'm going to call capital T of 1 is going to go like this. I'm going to take the vector and divide it by its magnitude. So I'm going to say 1 over the square root of 5, and then the vector is 1, 2. Remember, that's how we get a unit vector. If we want a unit vector in a particular direction, the direction of a given vector, we multiply the magnitude of that vector times the vector. Now, this right here is a unit tangent vector. And we say this is the principal unit normal vector, the principal unit normal vector. So this is a unit normal vector. Okay? So it's, and the word unit means it has a magnitude of 1. Okay, so this kind of gives you an overview of what we're doing. We're going to look at finding the unit tangent vector and the principal unit normal vector. But let's start off, and we worked here with at t equals 1. But let's just suppose we have a vector and we just want to get the general formula for the unit tangent vector. So we have this vector, and we want to find a unit normal vector. Now notice, so here if you notice, before I could write out what the unit normal vector is, the unit tangent vector is, I could say, well, the unit tangent vector, which I'm going to denote with capital T, is equal to the derivative divided by the magnitude. Of the derivative, okay. And of course, I mean, that's what we did. This right here is something that's worthy of a highlight. So let me put this around. This is one of the key concepts today. Now, I'm going to go ahead and find that vector. One of the things that you're going to encounter when you try to find these vectors, and particularly the normal vector, is you run into a little bit of algebra. So let's just go through the process of how we find the unit tangent vector. So here we go. First thing I need to do is figure out what r of t is. Well, it's 1, 2t. 1, 2t. And now I want to divide that by the magnitude. So the magnitude is going to be the square root of 1 plus 4t squared. That's the magnitude. So now at this point, if you're asked, show me the unit tangent vector, this is what it is. This is the formula for it. It goes like this. T is equal to 1 over 1 plus 4t squared, 1, 2t. So if you put in a 1 like before, you get exactly the same thing. You get 1, 2, and then this down here would be the square root of 5. But this is the unit tangent vector. And remember, it's, of course, parallel to the tangent on the curve. So this is where we're concerned about direction, and we don't want to we don't want to work with all different types of magnitudes. We just want a vector that points in the right direction. Now, are there any questions about that? Okay, now, what I want to do is I want to go to the next step now, because this is just, I think, pretty simple to understand. We're just going to take the derivative and divide by its magnitude. What I want to do is look at the principal normal vector. Now, if you think about it, now notice you might say, well, why did you say principal? Well, if you think about it, and we're generalizing here a little bit, but imagine a curve out here in space, and you get a normal vector. What you want is the principal normal vector. So we're looking at the principal normal vector of this. There are a lot of different vectors, a lot of different normal vectors, but what we're talking about is the principal normal vector. And this is a vector that's going to be on the same plane as the tangent vector, and it points inside the concavity. Now, let's just take a minute, and I want to kind of show you. First of all, let me tell you what the principal normal vector is. The principal normal vector is a vector that we denote this way. We're going to denote it with a capital N. And what it's going to be the derivative of the tangent vector over the magnitude of the tangent vector. Okay, so it's the same way, we get it the same way as we did the tangent vector. We just go one more step and we say, okay, I'm going to take that previous vector, find its derivative, and divide by the magnitude of the derivative. And this right here will give you the principal normal vector. Now, you may take issue with this. You may think, hey, how is that going to be tangent to the tangent vector? In other words, well, how is this going to be normal to the tangent vector? In other words, how is my taking the derivative of the tangent vector dividing by its magnitude going to give me a vector that's perpendicular to the tangent vector? So you may take issue with that. Well, let's just look at this a second and see. Let me see if I can convince you that that would be the case. Let's suppose that let's think about this. Let's think about this notion. Let's suppose that we have a vector. And let's suppose that I dot it with itself. Okay. Now, there's nothing. Now, if we cross product a vector with itself, we get a 0. But if we dot product a vector with itself, we don't necessarily get a 0. What we get, let's suppose that the vector is x of t, y of t, and z of t. Let's suppose that this is the vector. Okay. Now, if we dot this little fellow with itself, here's what we get. We get, whoops, it's not a vector. It's going to be x squared of t, right? In other words, we get x of t times x of t plus y of t times y of t plus z of t times z of t, right? Definitely, that's the cross product. Yeah, the dot product. Okay? Now, let's make this assumption. And we're just saying, so what I'm going to do is show you what happens if this is true. What happens if this is equal to a constant? So that's a special case we're looking for. Okay? Let's suppose that this is true. So here's what we're saying. We are saying that in this case, let's suppose that we do this dot product of a vector with itself, and it turns out to be just a number. What does that mean about this? Now, let me do this. Let me take the derivative of this. Okay? So I'm going to take the derivative of the dot product. So here's what I'm going to do. I'm going to take the derivative with respect to t of this dot product. Now, what do you know that equals? If the dot product, if it's a constant, what do you know that has to equal? It has to equal 0. That's right. So let me go ahead and take the derivative of this little fella here and dig this. This is pretty cool. We've got 2x. Don't forget the inside. Don't forget the chain rule. 2x of t, oh yeah, times the derivative of the inside, the chain rule, right? X prime. Can't forget that. 2y of t, y prime of t, plus 2z of t, whoops, 2z of t, times z prime of t. And we know that he has to equal 0 because the derivative of a constant is 0. So that's something we know to be true. Now, let me do this. Just divide out the 2. Because I've got a 2 every place, and I can divide the other side. So here's what we've got. X of t, x prime of t, plus y of t, y prime of t, plus z of t, z prime of t. Okay, and all that equals 0. If you look at this, that is a dot product. What is it a dot product of? What do you think? Yeah, look at this. Here's what we've discovered. This right here is actually the dot product of r of t and r prime of t. That's what that is. So I don't think anyone in here can argue with this if this is true. If this equals a constant, then we've just shown that this has to be true. That has to be true. There's no question about it. Okay. Okay, any questions about that? Now, let's go back and look at t. Okay, let's just look at t. What if we dot product t with itself? Is that going to be a constant? I think that's going to be a constant, isn't it? Because the game we could play is, well, we know a property of dot products that this right here is the magnitude squared. That's what that is. That's the magnitude squared. We know that. Okay, then if that's the case, then this is equal to 1 squared, which is 1. So that definitely equals a constant. Does everybody dig that? Okay, no question about it then. Then this is true. Then if we take t and dot it with its derivative, we for sure get 0. No question about it. Because we've proved that, right? Well, what does this mean then? What does that say about t and t prime? What do you think? If their dot product is 0, what does that mean? Yeah, it means they're 90 degrees, right? They're orthogonal. They're normal, right? You get a perpendicular. Okay, so when I said this, when I said, okay, the normal vector, remember, when I'm talking about the normal, I'm saying a vector that I can dot with the tangent vector and get 0. Well, apparently that vector is t prime. Okay, so if I dot t prime, I'm not finished yet. So if I dot t prime with t, I'm going to get 0, and that means they're normal to each other. Therefore, I can, if I want it to be a normal vector, I can just do this. Ah, look at that. Definitely, right? Anybody want to argue that? I think we got it, right? That's why this has to be the that's why this has to be the normal vector. Okay? It's soaking in. Okay, so this is the principal normal vector. Let me put a box around that. So we've got two big ideas, right? The unit tangent vector and the principal normal vector. The unit tangent vector, super easy to find, right? Now we're going to go back and look at this principal normal vector. Okay. Now, so let's go back. Oh, let me just insert here a new page. Okay. So here we go. We'll just go back to where we started. And we said this. We said that the tangent vector, the unit tangent vector was t over square root of 1 plus 4t squared and 2. Now this was t squared here, wasn't it? Sorry about that. This was 1. Messing up here. 1. And this was 2t. Okay. That's what we just dealt with, right? We had t comma t squared. We differentiated it. 1 on the top, 2t on the top, just the derivative, and I divide it by the magnitude. Okay. Any questions about that? And that's what we get. That's the unit tangent vector. Now, let's get the normal vector. the principal normal vector. Now, you have to be very careful, and you don't want to, now we're dealing with just the plane, so there's a shortcut to this, but I'm doing this on the plane so that we can kind of check our work. Okay, the first thing I know I need is I need t prime. I need to get that first. So that means I have two things to differentiate. I need to, first of all, differentiate the x component up there. And I'm going to call this 1 plus 4t squared to the negative 1/2. Right? That's what that is. Okay. So I'm putting on my differentiation boots. Make sure they're laced up real good. Okay, now I'm going to differentiate this. You want to go slowly, right? So this is going to be negative 1/2, 1 plus 4t squared to the what? Remember? Negative 3/2, that's right, times, don't forget the inside, 8t. Okay. So now let's just see what we got here. It looks like we've got a negative 4t, and down here, a 1 plus 4t squared to the 3/2. Okay, now y'all really watch carefully because I could get messed up here. Okay. Oh, whoops. Okay. Okay, so here we go. We got negative 4t, 1 plus 4t squared to the 3/2. Okay. Any questions about that? Okay. Now, I got to do this one. 2t, okay, over. So here we go. There's 2t over 1 plus 4t squared to the 1/2. Now on this one, I'm going to need to use the quotient rule. I mean, you could use the product rule on it by, writing that radical, writing the 1 plus 4t squared as negative to the negative 1/2, but I'm just going to use the quotient rule. Okay, so I'm just going to go very carefully here. I have the derivative of the top, which is just 2, times the bottom. Okay, there's that. Now, minus the derivative of the bottom times the top. So I'm just going to do minus, here's the top, and now I'll haul off and do the bottom. 1/2, 1 plus 4t squared to the negative 1/2 times 8t. All over this bottom squared, which is 1 plus 4t squared. Okay. Does anyone see any mistakes I made? You got to be careful differentiating. Keep your head on a swivel. A lot of things can go wrong, right? Any questions about that? Okay, now I like this. Look at this. That cancels. Good. Thank goodness. I didn't want to work with that 1/2. Okay, good. Thank you. Now, let's just see what we've got here. Trying to clean this up, and we don't want to get in too big of a hurry because we don't want to mess up. So this is negative 8t squared. And then we've got 1 plus 4t squared to the negative 1/2. Okay, that all worked. That all went well. I feel good about this so far. Okay. Now, there's a trick that we've always used that if we want to get rid of this negative 1/2 power here, just multiply through by 1 plus 4t squared to the 1/2 power. Because then when you add the negative 1/2 to the 1/2, it goes away. It's 0. So the whole radical here goes away. And here's what you get. Up top, you'll get a 2 times 1 plus 4t squared to the first power, right? 1/2 plus 1/2 is 1, right? That's from right there. Over here, I've just got minus 8t squared. Because if you add 1/2 here, you get 0. So 1 plus 4t squared to the 0 is just 1. Now down here, we've got 1 plus 4t squared to the 2/2 plus 1/2, that's 3/2. There that is, okay? Everybody good with that? A lot of algebra. Here we go. Stay with me. Now, I'm going to distribute through the top, and it looks like what I'm going to get, well, let's just go ahead. I've got 2 plus 8t squared minus 8t squared. Hot dog. Look at that. The t's are going to cancel, the t squared, that is, which is nice. And now we've got something fairly manageable. We've got 2 over 1 plus 4t squared to the 3/2. So I'm going to put that up here. What was it? 2 over 1 plus 4t squared to the 3/2. Is that what I had? Now, that right there is the derivative of the unit tangent vector. But it's not the principal unit normal vector, right? This vector is normal, but it's not the unit normal. And we want the unit normal. So you know what we got to do? We got to divide by the magnitude. Yeah, the magnitude. That's what we got to do. Okay, so let me get the magnitude now. Now, I wonder if I can copy this. I'm really risking it here. Maybe I can I copy that? Ooh, I can clone? No, undo that. Let me just copy it. And maybe paste it down here. Let's see how this works out for us. Ah, hey, look at that. Okay, now what I want to do is get the normal. I want to get the magnitude. So here we go, the magnitude. Okay, so here we go. It's going to be this. It's going to be 16t squared over 1 plus 4t squared to the 3rd. Now remember, there's a radical around this. Don't forget that, right? Okay, so I squared that plus 4 over 1 plus 4t squared to the 3rd. Okay, that's the magnitude. Now, fortunately, we have the same denominator, so that makes it nice. So let's see what we've got now. See if we can clean it up a little bit. I've got 16t squared plus 4 over this thing. Okay, any questions about that? Okay, now, what would you do next to simplify this radical a little bit? Yeah, 4, brilliant. Yes, I would take out a 4, and then look what you got. The square root of 4 is 2, so I've got 2 square roots of 4t squared plus 1. And let me just go ahead and take this out of the radical down here and call it 1 plus 4t squared to the 3/2. There's what we've got, right? That's the magnitude. That's the magnitude right there. Okay. Oh, yeah, you could. That's right. That's another thing. So I guess we can go another step with this, right? So what is this going to be? This is going to be 2, and this is going to be 1 plus 4t squared to the 1/2, right? Oh, it's to the first, isn't it? Because look, well, this is 1/2. So look, we say 1/2 minus 3/2. That's going to be -2/2, so it's just 1, right? Okay? So that looks even better, doesn't it? Okay? Now, let's do this. Let's go back now and talk about, let me get a new color here. Let's go ahead now, we're ready to talk about the principal unit normal vector. So here we go. Let's see what we've got here. I've got, well, remember this is going to be t prime over the magnitude, well, t, the magnitude. Okay. Now, I'm going to just multiply by the reciprocal, okay? Just multiply by the reciprocal. So I'm going to go ahead and pull it inside here, and look what we've got. Let's go up here. We've got -4t over this. So here we go. This is going to be -4t over 1 plus 4t squared to the 3/2 times the reciprocal. Okay, like that. Just trying to save some space here, save a step. Not too much, though. And then we've got this one, 2 over 1 plus 4t squared to the 1/2. So let's go this. 2 over 1 plus 4t squared to the 3/2. And we're multiplying it by the same thing. Okay, any questions about that? Okay, now here's what we want to do. I'm going to just simplify this now, and I'm going to get my principal unit normal vector. So this is going to be, up top we're going to have a -2t, right? And what's going to be on the bottom here? Yeah. And then this one over here is just the 2's are going to cancel. And it looks like we're going to have 1 over the same thing here. 1 plus 4t squared to the 1/2. Okay. Does everybody see that? Now, if you look up here at the, what was the tangent vector? The tangent vector was this, right? And you notice what's happened, and this is always going to happen on the plane. The y came over into the x spot, right? The y came over into the x spot, and the x went over here, and I changed the sign. One of the signs got changed, right? So, look, here's what's going to happen. Let's suppose that this right here is the unit tangent vector. And you have x of t, y of t. Let's suppose you have that. Then the principal normal vector is going to be one of two options. You're going to have y of t and then x of t here. And you're going to change that sign, right? Or what's the other option? What do you think is the other option? What would be the other one? So we could have this. We could have y of t and negative x. Those are the two options. Now this is if you're working in the plane, right? this is the way it's going to work. And you notice, if I dot product these two, I do get a 0, right? Is that right? These two. Okay, if I dot product those or if I dot product these, either way I get a 0. Okay, how's that? Any questions about that?